I hope you can hear me well and also see me well and see the slides too. Good morning, everyone. Welcome back to this 11th webinar in this energy data modeling program by the IEA. Today's topic, as you know, is SDG 7.1 with the topic specific focus on solid biofuels, clean cooking, and electricity access. Just a quick reminder of our overall agenda. Today, we will finish, let's say, with this week, the third lecture we had this week. And next week, we will have solid biofuels estimation model lecture, in which we will have one of our consultants that will be leading the overall webinar. And then on Thursday, we will have a wrap-up quiz and closing session in which we will be asking you some questions related to the topics that were addressed during this program, this first phase actually of the program. And then we will continue with phase 2 probably in the next months, depending also on policies on travel, etc. So today we will focus more into details into the following topics. So first, we will enter into the case of solid biofuels. As we all know, solid biofuels are very important in Sub-Saharan Africa, but there are many barriers and difficulties when it comes to collecting data and treating statistics for solid biofuels. Still, there are available interesting analysis on those practices and also on clean cooking numbers. So we will end this part on the on-site biofuels and cooking by looking ahead of potential outlooks and modeling principles to try to assess what the future could look like when it comes to the consumption of solid biofuels. Or, for example, also when it comes to the number of people actually which have currently access to clean cooking fuels, because this is actually what SDG7 tries to measure as an indicator. And as you know, the goal of this SDG is universal access to clean cooking on one side and access to electricity on the other side. So we will break then after this introduction to solid biofuels and, as I said, access to clean cooking. We'll have a Q&A session, and we will do a small exercise focused on these specific aspects, so on modeling of access to clean cooking, really probably simpler exercise if compared to the ones we had in the previous lectures together. So in the second half of this today's lecture, we'll discuss access to electricity, and we will have a specific focus on off-grid electricity access. We'll go through an overview of this topic. We'll discuss data and statistics, again, on electricity access. And to conclude, we will have a look on at the modeling implication on access to electricity. For example, how can we, for example, do long-term projections of electricity access, and what could the future look like in terms of required investment, for example, for giving access to electricity, for giving universal access to electricity, or, for example, what are the CO2 emissions related to, for example, new connections and more people, actually millions of people gradually gaining access to electricity. So which are the CO2 emission implication? Because we also have another SDG, SDG 13, which is focused on climate change. So we also always have to have in mind also this aspect. So before moving with the actual lecture, I would like to ask you to, as usual, connect to www.menti.com. I will pass the link in the chat so that we can have, as usual, a brief live polling. Let me just copy in the chat the link so that you can access it directly. You can do it from your laptop, from your mobile phone. The link is that one that you find in the chat. I also copy paste the code. Okay. So I hope you're all able to access the website. In the meantime, I will start reading you the first question, which is how many kilograms of wood do one need to produce 1 kilogram of charcoal in a traditional earth kiln? You have three options. You have 2 kilograms, 5 kilograms, and 10 kilograms. So I will wait a bit. This okay. I already see some answers, so it means that some of you were able to connect. You see two answers. Okay, three, perfect. I remind you, this polling is completely anonymous, so as usual, feel free to answer the way you prefer, the way you think is the correct answer. Actually, in this case, we can just see an aggregate, so how many people answered each option. So 5, let me check with respect. Okay, so okay. Few seconds more for the last maybe people which were still connecting. Okay, so okay, perfect. I see that the vast majority of you answered between 5 and 10. Actually, both these answers were correct. Actually, it depends really on the efficiency of the earth kiln you are using. So in particular, we have both, like based on our data, on our assessment on the overall continent, we have different values ranging from 5 kilograms to 10 kilograms. It really depends on the efficiency, as I was saying. But for example, let's say the most traditional ones between the different kind of hard kiln that are available across the continent have, for example, 10 kilograms as in terms of kilograms needed of wood in order to produce 1 kilogram of charcoal. So this is more or less the range, let's say. So in this case, we have 10 as a correct answer, but also 5 was correct. It really depends on the efficiency, and that's really a context specific, let's say, information. So let's move with the second question, which is a ranking question. What you're asked is to rank the best solutions for achieving universal access to clean cooking. You have 5 options. So you have LPG, you have electric cooking, you have biomass improved cookstoves, you have biodigesters, so which use biogas, produce biogas, and a combination of all these options. So which of these 5 is like starting like with a ranking approach, but you have to start with the best solution in order to achieve universal access to clean cooking, and then go till the last one. Okay, I see one person answered. I give you maybe a bit more time, since we know that ranking questions are a bit, you have to actually think about all the options and click all of them. So you see right now we have 3 answers. LPG is the first one. We have both electric cooking. Okay, now we have, okay, biodigesters. Okay. Okay, so I think more or less is the number I was aiming to. Aiming at. Actually, here there is no, let's say, correct answers. Um, Probably the best answer would have been a combination of all these options, because since here we are asking you what's the best solution in order to achieve universal access to clean cooking, it's difficult to say that one technology will be the one which will, let's say, guarantee to the overall, to the entire continent, universal access to clean cooking. So the idea is having a combination of all the possible clean cooking solution options that we have. So for example, if we don't have access to clean cooking, maybe we can start providing improved solid biofuel stoves. Then on a second step, we could have LPG stoves. And then, for example, if we are in areas in which we have access to electricity, we can provide electric stoves. So the idea is that all of them are considered by us, by the WHO, so the World Health Organization, as clean cooking solutions. The idea is to have an holistic approach, like an overall approach, and depending on the context, to select which is the best solution to use. So, for example, if you don't have electricity access in one community, one city, or like a specific household doesn't have access to electricity, clearly electric cooking wouldn't be the best option. Maybe we would go with the other options from this list. On the other hand, when we have electricity and let's say it's the using of electric cooking is affordable, for example, for a specific household, etc., then we can go to electric cooking option. So it really depends on the context, but take into consideration that all these options are a piece of a puzzle through which we can aim at achieving universal access to clean cooking in the African continent. So that's it for now. We will come back to Menti later during today's webinar. So right now, as I introduced, we will start with clean cooking. So I will share my screen and let me know if there are any issues with the sound or the video.
Let's get started with solid biofuels and access to clean cooking. We will look at the importance of solid biofuels in Sub-Saharan Africa. Solid biofuels is an important and useful energy source in most African countries and is used primarily for cooking purposes and then for producing electricity. First, there is the cultural preference of some people who prefer to cook using firewood traditionally, but there is often an accessibility issue in rural areas for other sources of energy such as LPG, and so firewood is usually the most accessible fuel for cooking. In urban areas, even if modern fuels can be accessible, we might have the issue of affordability as these modern fuels are more expensive than wood. So even if alternatives exist, people still continue cooking using biofuels. Now let's see what are the impacts of using solid biofuels. The use of solid biofuels is not without consequence for the health of the population. Studies have shown that more than 500,000 people die every year from pollution from biomass cooking. This is more death compared to diseases such as HIV, malaria, and tuberculosis. Other drawbacks of using biomass is that women also suffer from wood collection and spend several hours daily picking biomass. There are also safety consequences as they usually go alone in the forest. If the use of biofuels and wood is not done in a sustainable way, then there are negative impacts on the environment. If there is no balance, then the forest is reduced. It is also important to collect good biofuels data for policy making in order to guarantee that we ensure clean cooking access, proper regulations for charcoal production, etc. Therefore, tracking biofuels production and consumption is key for countries in sub-Saharan Africa. Now, let's put things quickly into perspectives and see how energy demand has evolved over the years. In 1919, wood accounted for around one-third of total energy demand. Over the years, we see how energy demand transitioned to oil, natural gas, etc. The share of wood decreased a lot at global level, decreasing from 30% in 1919 to only 4% in 2017. But in absolute value, biofuels rose by two-thirds from 400 mtoe in 1919 to 650 mtoe in 2000. Since 2000, as developing countries move away from the traditional use of biomass, the absolute consumption drops from 650 mtoe in 2000 to 620 in 2018 and 550 in 2040 based on the stated policy scenario. Now, if we look at final consumption, we see that in OECD countries, biofuels and waste is not significant, and in non-OECD region as well, it accounts for only 15% of consumption. However, if we look at Africa, the share increases to over 50%. And in sub-Saharan Africa, it is even larger, accounting for three-quarters of total final consumption. We have seen that biofuels are the highest consumed fuels in sub-Saharan Africa. In sub-Saharan Africa, the biofuels consist mostly of primary solid biofuel such as wood and then charcoal. Now let us see more in details what we include under biofuels and waste. First, it includes primary solid biofuels such as wood, but also biogases, charcoals, bioliquids, as well as industrial and municipal waste. In OECD countries, we use mostly modern biofuels and also bioliquids such as biogasoline, biodiesel, and bioethanol. These are mostly used in transport, whereas for waste, they are usually used for electricity generation. Now, if we look at Africa, we see that it consists mostly of primary solid biofuels and charcoal that is considered as traditional use of biomass. And in sub-Saharan Africa, it is even more primary solid biofuels. Now, let us see more closely at what are solid biofuels. Solid biofuels covers organic, non-fossil material of biological origin. We can make a distinction between primary and secondary biofuels. Primary production is the capture or extraction of fuels or energy from natural energy flows, the biosphere and natural reserves of fossil fuels within the national territory in a form suitable for use. Inert matter removed from the extracted fuels and quantities reinjected, flared, or vented are not included. The resulting products are referred to as primary product. Secondary production, on the other hand, is the manufacture of energy products through the process of transformation of other fuels and energy, whether primary or secondary, such as charcoal. Only the amount specifically used for energy purposes, that is a small part of the total, are included in the energy statistics. Let's see how solid biofuels consumption is evolving in different regions. First, we see that in 2018, Sub-Saharan Africa accounts for one-third of total solid biofuels demand, and if we look from 1990, we see a constant increase in demand that nearly doubled in the last 30 years. In the rest of the world, demand has remained quite stable. This shows that we are still increasing the use of biofuels, and access to clean energy sources are slower than population growth that is increasing very fast by 3% annually. But where are solid biofuels consumed? In which sectors? In OECD countries, less than half is used in residential sector, mostly for heating purposes, and a big part is also used in industry for raising heat in industrial processes. However, in non-OECD, a big chunk is used in the residential sector. If we go to Africa, most of the solid biofuels is used in the residential sector and for cooking purposes. However, these numbers could be lower or higher because of data uncertainty. This graph shows household consumption for cooking purposes in rural and urban areas. And we can see clearly that there are some differences between rural and urban consumption patterns for fuels. In urban areas, we have a bit more fuel mix for cooking, where we have some use of LPG, kerosene, and electricity. However, in rural areas, it is still primarily fuel wood and charcoal. We often know how much kilo of wood that we collect, but how much energy does that wood contain? This is one of the barriers of biofuels data collection. The net calorific value, it's the useful energy, and the moisture content is also very important. Depending on how moist the wood is, the calorific value varies. Normally, when you cut or collect wood, it has a moisture content of around 55%. But if you dry the wood and reduce the moisture content to only 20%, then you see that the calorific content is more than twice than the wood with a moisture content of 55%. The efficiency of the combustion will be more, and it will be also more healthy. Now, if you transform the wood into pellets, then the calorific value is even higher. It is often the case in Africa that the wood is used fresh because of lack of space for storing and also the danger of being stolen. So in Africa, the average net calorific value of wood is around 7 megajoule per kilogram. And note that for comparison, that for LPG, it has a net calorific value of 50 megajoule per kilogram. So there's a big difference between the two. The production of charcoal is an output of a transformation process where wood is considered as the input. Note that the calorific value of charcoal is much higher than firewood. Note also here some important facts about charcoal production. The efficiency of the charcoal kiln varies quite a lot from 10 to 40% depending on the technology used, and in sub-Saharan Africa this is often very low. To produce 1 kilo of charcoal, you need a lot of wood, and in energy units the efficiency can be as low as 20%. But if you have good wood, why do you need to transform it into charcoal? Charcoal is a better energy product. To have the same energy as 1 kilo of charcoal, you need to burn 2 kilo of dry wood. However, if you use moist wood, then you will need even more. Often in Africa, firewood is consumed without drying because storing it might mean it will be stolen and there's also not space. So its quality when burned is lower. Firewood net calorific values are very variable depending on the type of wood and the moisture content when it is burned. In average, we can assume that it is 14 megajoule per kilogram. Charcoal, on the other hand, is a higher quality energy product with a calorific value of around 30 megajoule per kilogram. So it is more practical to store and transport charcoal because with the same energy, you need less volume and weight. However, the transformation of wood into charcoal has a lot of impact. To produce 1 kilogram of charcoal with traditional earth kiln, you need up to 10 kilo of wood. So you need a lot of wood and so a lot of trees. Therefore, it can lead to deforestation if it is not done in a sustainable way and will affect the environment and lead to deforestation. However, with an improved kiln, it can be better and the yield efficiency is around 30%. And you can also use charcoal in an improved kiln to produce biofuels and let us look even more at the end use energy service that is cooking. Here we will see the different type of fuel, so wood and charcoal, and the means for cooking that is traditional stove and improved cook stoves. With a traditional stove, you need around 5 kilo of wood to cook a meal. But if you use charcoal, you need only around 1.65 kilogram of charcoal. Then to produce this charcoal, you will actually be consuming 16 kilogram of wood if using an earth kiln. So in the end, when you do a complete analysis, you are actually consuming more wood. The life cycle analysis shows an efficiency of 5% only. If you use an improved kiln to produce the charcoal, you are actually using around 6.7 kilogram of wood to produce the charcoal, and the life cycle analysis shows an efficiency of 14%. In an improved cook stove, you need just 3 kilogram of wood to cook a meal, which is better. And if you use charcoal in an improved cook stove, you need even less, that is only 1.15 kilogram of charcoal. If that charcoal is produced in an earth kiln, you will need 11.5 kilogram of wood to produce the charcoal, and the life cycle analysis gives a real efficiency of 7%. In an improved kiln, you need only 4.6 kilogram of wood, and the life cycle analysis or value chain impact is better and gives you 19% efficiency. Therefore, even if charcoal cooking is more efficient than wood cooking, at the end use stage, the impact on wood resources and deforestation can be much higher. With the increasing urbanization, the demand of charcoal could drastically increase if sound policies are not in place. Why do we have this impact on climate? If you have a forest, this forest is absorbing CO2 emissions and storing the carbon in the wood. Now, if you cut the wood and burn it, we release again CO2 emissions. And if we do this in a sustainable way, we have net zero emissions. And if there is an equilibrium, there is no net emissions. However, if the amount of wood is not cut in a sustainable way, that is, we cut too many trees, then the amount of CO2 released from burning the wood will increase drastically. And at the same time, the forest too will diminish, leading to a disequilibrium, and we will end up with positive net emissions as the absorption of the forest is much less. So if there is no net equilibrium, we have net emissions, which is positive. Now, let us move to the second point on the barriers and best practices for collecting solid biofuels. For biofuels, if we focus on primary solid biofuels, we see that all the products are combustible energy commodities which can be traded and stocked. The consumption of these products will be either as a transform to secondary product or as blended to the other sources or used directly in an end-use application. But how do we get these data? We get them from sales data, for example, from wood and charcoal sold in markets and consumption data. But here we also lose a big chunk of data as we miss the black market sales, and also some people pick wood directly in the forest and so do not buy it. What are the common barriers? As you have seen, we have this issue of commercial and non-commercial fuels. But we also have a need to have a correct sample, and it is important to work with the statistical office of your country to have a representative sample for both urban and rural areas and also by regions. We need to collect data by type of solid biofuel used, as regional wood resources are different with different calorific values and moisture content. There is also the cultural difference to take into account because different people cook in different ways, etc. There's also different types of appliances, different cooking stoves. We need to cover both commercial and non-commercial biofuels and include charcoal as well. For non-commercial, we need to track how much wood is picked, the reselling, also the unregulated charcoal production. There is also a need to understand how charcoal has been produced in order to estimate the fuel wood input. So what type of kiln has been used? So is it traditional kiln or improved ones? Now, let us see what tools we have at our disposal to establish a methodology or an action plan to track residential consumption and biofuels demand. For the observed data inputs, we can find information from administrative data, surveys, and measurement. Using those input with some assumptions of calorific values, uh, consumption of stoves, and energy by device, we can derive some estimations using modeling in order to have complete data output for energy by source, by end use, and also calculate indicators. Let's see a bit more the tools and data needs. This is not perfect, but we try to give relevance to each one. For example, if we leave it blank, then it means that it is not the best practice. But if it is green, it means that for this data this is the preferred data source. Estimation and modeling. Here we have to be careful as consumption patterns change, and we can't just assume that people consume in the same manner as 20 years ago. So there is also access to clean cooking to take into account. Note that it is important to continue collecting resources data, that is forest data, as well as charcoal production by type of plants. It is essential to track how sustainable biofuels consumption is. Now let us go even deeper into an action plan for solid biofuels data. How will we start? In 2010, let us assume we have a survey for household consumption by type of fuel. And we also know that the number of households. And with this information, we can calculate the total of charcoal, fuel wood, and LPG. Then for the next 5 years, we don't run any surveys and we just use qualitative data from census. Then we can estimate the missing years, but beware that we cannot use the estimate for many years as they lose their value over time. So if we use the qualitative data and add it with the number of household by type times the intensity, we can calculate for 2011 up to 2015. In 2016, there is another survey that is done. And here we will get observed data, and this will also permit us to revise previous data, estimated and old surveys data if we collect even more detailed data. Survey results help us calibrate qualitative data for estimations. It is true that surveys are costly, but it is even more costly not knowing what is happening. Now we are going to deal with the last part of solid biofuels, and we will look at clean cooking status and modeling. Solid biofuels in developing countries are mainly used for cooking, a topic covered under the Sustainable Development Goal 7. There is the first target, which is 7.1, that ensure universal access to affordable, reliable, and modern energy services. And we have the indicator 7.1.2, which is the proportion of population with primary reliance on clean fuels and technology. How do we define clean cooking facilities? We have several technologies for cooking, and we define as not clean cooking technologies when we use biomass, coal, and kerosene. Note that for biomass, only the traditional use of biomass is not clean, and if you use an improved stove, it is clean. With this, we can calculate access to clean cooking. There are some complications to understand that, but because when you use an improved cook stove, there are different types with different efficiencies, and they also release smoke in different ways. So there is different CO2 emitted. For example, a basic improved cook stove uses between 20 to 40% less fuel than a traditional cook stove. But if you use an intermediate cook stove, you can reduce up to 60%, and an advanced improved cook stove, you can reduce by 50 to 70% fuel consumption. Same for smoke release, it can vary considerably. Therefore, it is important to know which cook stove a household is using, as the impact is different. Some people use different cook stoves for different meals cooking in the same household. So the task is even more complicated to collect all this information. At the IEA, we have tried to analyze the trade-offs between the different cooking fuels and technologies and gave them a score based on different criteria. There is the stove cost, so the traditional biomass is most advantageous because you just need to put free wood. For fuel costs, here you have to pay for electricity or LPG, and this is a disadvantage because here we have a problem of affordability. Then we take into account reliability, health impact, because if you are not using clean cooking fuels such as coal, this is a disadvantage for health. There is also the gender inequality, as it is mostly women that collect wood for cooking, and there is also the environmental impact to take into account. Now, let us look at an analysis that the World Energy Outlook team did on the status of access to clean cooking and tracking progress of what has been done lately. Globally, the average number of people without access to clean cooking has been stable since 2000. But if you look at Sub-Saharan Africa, the share has been constantly increasing, and in 2018 it reached 35% of the world. This is because population has been increasing faster than tools to help people access clean cooking facilities. The IEA has been working on energy access issues on the continent for nearly 2 decades. Africa's population is among the fastest growing and youngest in the world. The situation for clean cooking is more concerning, as the number of people gaining access barely exceeds population growth. Population relying on traditional use of biomass, kerosene, or coal increases from around 900 million people in 2018 to nearly 1 billion people in 2030. This has grave health, social, and environmental consequences, and the resulting household air pollution from traditional uses of biomass continues to cause 500,000 premature deaths a year. Now, why do we need to make projections for cooking? Making projections on access to clean cooking and on cooking fuels enable us first to estimate the number of people with clean cooking and track the SDG 7.1 indicators. It also helps us to better understand the future energy demand based on the portfolio of cooking technologies. It also helps us anticipate the supply of cooking fuels and its related investment. And finally, it helps us to assess the impact related to cooking, the health, climate, and environmental impacts. This is an example of fuel wood consumption and its impact on forests based on two IEA scenarios. The stated policy scenario is the scenario that is based on countries' announced policies, and the Africa case, it's a new scenario that achieves the continent's inclusive and sustainable vision for accelerated economic and industrial development, accompanied by the achievement of full access to electricity and clean cooking. Fuel wood consumption up to 2040 in the stated policy scenario keeps increasing in all these countries, and the forest keeps depleting. If we don't do anything, the impact on the environment will be terrible. However, in the Africa case, consumption of fuel would decrease, and so does the impact on forests because of less wood being cut. This is linked to an accelerated move away from the use of solid biomass and to the wide application of energy efficiency policies. The shift in the energy mix away from biomass towards modern energy sources such as renewable and natural gas results in major efficiency gains and accelerated uptake of other fuels for cooking. For example, cooking with LPG uses around 5 times less energy for one meal than cooking the same meal with traditional use of biomass in inefficient stoves. Now, let us see some of the key principles for modeling clean cooking access and the general principles for modeling as seen in the modeling sessions before. We need first to analyze the drivers such as population and cooking practices. With the drivers and some econometric analysis, we get the energy services demand, which is the useful energy demand needed to cook a meal. To cook, you need a portfolio of cooking fuels and equipment. You have to do a technology fuel reallocation. You can do a cost-based approach as well. So how many households will be cooking with LPG, will be cooking with traditional use of biomass, etc. in the future? Based on the efficiencies of these technologies and the useful energy demand, you can then calculate your final energy demand. And you can also calculate the amount of energy needed to produce in the country. The challenge here is how to allocate the technologies to population. First, not all households have access to clean cooking technologies. Therefore, we need to look at service demand separately for those who do and do not have access. For those who have access, there is a wider choice of technology and fuel based on fuel availability, cost, cultural preferences, etc. For those who do not have access, the choice is restricted and limited to the cheapest and free options and whatever fuel is available locally. Other options not available or not affordable, therefore they choose the traditional use of biomass, kerosene, or coal. We also need to look at how the number of people with and without access may change and what can drive this change. So, with policies and market evolutions based on characteristics of each fuel equipment, and also how and when will they gain access and shift to cleaner fuels and equipments. With all this information, we can derive the number of people gaining access. Let us look at some of the results that the IEA got based on analysis done. Our analysis showed that in Sub-Saharan Africa, the number of people without access to clean cooking will not decline drastically by 2030 in the stated policy scenario, which is the objective of the Sustainable Development Goals. So this scenario does not provide the right tool to achieve full access by 2030 and fix the affordability issue and the change in cooking habits. However, in the sustainable development scenario, where we achieve full access by 2030, we see that Sub-Saharan Africa, which in 2010 had less than 20% access to clean cooking, will reach full access by 2030. But how is this done? In 2018, 87% of the population in sub-Saharan Africa still lack access to clean cooking, and the fuel mix still has a lot of not clean fuels. In the stated policy scenario, more people gain access to clean fuels and technologies for cooking by 2030, but 70% of the population still lack access. To bridge the gap and achieve full access to clean cooking for all in the Africa case, LPG is the most scalable solution for urban settlements, with improved biomass cook stoves doing most to provide access in rural areas. LPG is the best solution as more than half of urban households gain access by 2030 as the population density justifies investment in the necessary infrastructure. In rural areas home to the majority of those without access, improved cook stoves are by far the preferred solution, dramatically improving the efficiency of bioenergy use. Electrification, biogas, ethanol, and other solutions also play important roles with their uptake depending on local context. Policies will continue to remain essential to push these solutions. In Cote d'Ivoire, for example, the national plan seeks to promote LPG use and increase efficiency of charcoal production. Therefore, despite progress in several countries, current and planned efforts to provide access to clean cooking barely outpace population growth.
Okay, perfect. So I think you were able to hear and everything was clear. If you have questions, as usual, also during the webinar, feel free to ask them. But now we will have a dedicated question and answers session. So feel free to write in the Q&A box, in the chat, or to raise your hand so that I can give you the floor. Otherwise, we can, in parallel, continue also with another mentee.com polling. So in the meantime, if you want to think about, I don't know if you have questions, etc., I will put again in the link in the chat the link to the mentee.com polling, so that maybe also some of you which joined lately, which aren't able to see the previous messages, can join us too. So I will move to the next question. I will wait a few seconds for you to log in to mentee.com. In the meantime, I will just anticipate you the next question, which is, it's not like there is no right or wrong answer in this case. It's just a polling question. We want to ask you, in your household, what fuels do you use for cooking? So pay attention. We are asking fuels, so plural. So maybe some of you, as I already see, one person at least is using both charcoal and LPG. So you have 5+1 categories. So you have wood, you have charcoal, you have LPG, you have electricity, and you have kerosene, and then you have others. So just tell us which are the fuels you use usually for cooking in your household. So in this case, I see LPG is the leading technology, the leading fuel in this case. Then we have charcoal. Apparently, no one is using electricity, neither wood and neither kerosene. I see 4 of you answered. We'll give some seconds more for the rest of you, which maybe are still logging into mentee.com. Okay, I see an additional person which is using both charcoal and LPG. So it's good that first I see kind of many of you which are using 2 technologies. Also, if you want to give me some insights with respect to this, like why are you using 2 fuels? Is it because each specific fuel is used on in order to fill like some specific cooking needs? So you have things that you prefer to cook with charcoal and other stuff that you prefer, other meals you prefer to cook with LPG? Or is it also based, I don't know, on the price of both of these fuels, which may vary during the year, during the months, depending on the international and local markets? So feel free to give me insights on that. I'm definitely curious. Okay, I will move on with the next question, which is, what is the electrification rate in Sub-Saharan Africa? What was actually, because this survey was prepared a few months ago, in 2019 in Sub-Saharan Africa. So you have 3 options. You have 45%, you have 70%, and you have 55%. What do you think was actually in this case the electrification rate in Sub-Saharan Africa? So how many people do you think had access to electricity? Because now we are moving to the next phase, which is focused on electricity. So how many people, which percentage of the population you think had access to electricity? Okay, I see 3 of you, 4 of you selected 45, 1 person 55, no one actually selected 70. So I guess you think it's too much. Okay, so let's discover which is the correct answer. The correct answer was actually 55%. So 55%, clearly in this case, we are talking about Sub-Saharan Africa, not the entire continent. And this has been increasing clearly, because we are talking about electrification rate, even though we had a slight decrease and because of the COVID pandemic, we noticed through our analysis that many people in the continent at a certain point, even though they were, for example, connected to the electrical grid, because of the impact on the economics of the pandemic, weren't able actually to afford to pay the bill, and so they were actually in our World Energy Outlook, they were classified as not having access to electricity. And here it's important to see that we are talking about a continent in which the population is growing very much. So it's important to have also the access rate, which is also growing, in order to keep to be able to be faster, let's say, because otherwise we would have many people actually being born and at a faster rate than those people which are gaining access to electricity. So we would have on the long term lower, let's say, impact of the electrification programs across the continent. Clearly, this is really country specific, because if you go, for example, on our website, you will have a map of the entire continent, which you can see the different rates for each country, with the disaggregation also between urban and rural. So it's really different from one country to another. But clearly, this was a general consideration on the overall continent, also because the population growth rate changed country by country, but it's really high on the entire continent, especially if compared to other countries on the northern part of the world, let's say. Okay, so I will continue with the next question, which is which region do you think concentrates most people with no access to electricity? So you have India, other Asia, you have Western Africa, you have Central Africa, you have Eastern Africa, and you have Southern Africa, and you have the rest of the world. So just rank them. Again, this is a ranking question, so I give you a bit more time. You have to rank these areas, starting from the region you think has more people, so the most people with no access to electricity. So we are not talking about access rate, so in terms of percentage of their population, we are talking about how many people actually, in terms of million, there are in these areas which don't have access to electricity. So which is in this area, among these areas, the area with the most people with no access to electricity in terms of million of people. Okay, I see two people voted. I see India, Eastern Africa, Western Africa. Okay. Okay. Okay, I see India right now is the first one. Then we have Eastern Africa, we have Central Africa, we have Western Africa, Southern Africa, other Asia, and the rest of the world. So actually, the correct answer was, at least looking at the first one, was Western Africa, which is the area in the world in which right now we have mass majority of people not having access to electricity. So let's continue with the next question, which is what percentage of health centers does not have access to reliable electricity from in your opinion? So again, we are talking about just Sub-Saharan Africa. So in terms of percentage, how many, so which percentage of health centers does not, so we are asking you, are not connected to, so don't, do not have access to reliable electricity. Pay attention, we are talking about reliable, so it doesn't, it's not enough to be connected to some sort of electricity supply, but here we are talking about a specific dimension of having access to electricity, which is the reliability. So why do we are interested, or why are we interested in this specific aspect when talking about health centers? This is because we all know the benefits of having health centers with reliable access to electricity. And it's really important to guarantee that these social services have access to electricity, ideally 24/7, so for the entire day and during the week and during the year, because of the service they provide to the community they are, which refers to them. So in this case, I see three of you answer, so 35%. Two of you answered 60%, and just one of you answered 75%. So actually, the correct answer was 60%. And this is based on 27 sub-Saharan African countries. And this is a study from 2018. So apparently 60% of the health centers in sub-Saharan Africa does not. So 6/10 health centers in sub-Saharan Africa does not have access to reliable electricity. Next and last question is, in your opinion, which are the best solutions to achieve universal access? So let's say that you have 100 points to distribute according to importance, and you have these four options. So we ask you which between grid extension, grid densification, mini grids, and solar home systems. So you have 100 points and you can distribute them among all these four technologies and solutions, let's say. So you could distribute it equally. You could decide to go 100 on just one technology because you think that one is the winning one, let's say in this portfolio of options, or you can do your consideration. So the idea here is to answer, like to distribute these points based on your opinion with respect to which are the best solution to achieve universal access. So first, think about these four. whether all four are important. Okay, already we have an answer. Okay, perfect. So we have one person which says that 60% importance, like he had 60 points accounted to the grid extension. Like think about having about those 100 points to be a budget, and you can decide, for example, to allocate this budget to the specific to program dedicated specifically to each of these technologies, and try to think how you would ideally distribute this budget. That could be, for example, a country budget, how you would allocate it across these four technologies, these four solutions. Okay, I see the grid is the winner right now. By far, actually, we have the second place, solar home systems, then we have mini grids, and we have grid densification. Okay, a few seconds more, I leave you for the last of you which didn't answer yet. Okay, we lost a bit of grid extension, a bit more on grid densification. This is clearly the average between all your answers. Okay, so I won't give you, because actually there is no correct and right answer, but lately during the okay, the presentation, you will see how also during how when we do modeling, we calculate the impact and the potential impact those for example, solutions could have on the continent, especially when talking about people not having access to electricity in Sub-Saharan Africa. So this was it. Before moving to the second part, which, as I said, is focused on access to electricity, I wanted to have a look with you at the exercise we have for this today's lecture. So going back to the beginning, you should be able to see right now my the handbook for Rwanda. So the Statistics and Modeling Training Handbook. As you know, you can go to page number 2, in which you have the table of content. You can go to page 40, in which we'll have today's exercise. Oh, sorry, I don't think I'm sharing actually. Okay, now you should be able to see it. Page 40, you have the exercise, let's say the clean version, so you don't have the solution. And then at page 101, you have the same exercise, but with the solution. So right now, as usual, we won't go, let's say, through the, we won't do actually the exercise. It's just to have an overview of the methodology, the approach that you can have while trying to solve it. And then I invite you to try to do it by yourself after today's lecture. I don't know if some of you already tried to do it, if everything, let's say, went smoothly. If you want to ask me anything with respect to the methodology, the procedure. So in any case, feel free to do it right now. Feel free to send me an email later, and I will try to support you in whatever problem you may have. So let's go directly to the exercise. Just 1 second so that I close. Okay. So you have been asked, as usual, this is an exercise in which you have to, an hypothetical situation in which you are asked by some entity, the vast majority of the time is the Ministry of Energy of an hypothetical country, because here we are using random data, like realistic data, but which don't come, let's say, from one specific country. So you have been asked to assess the cooking technologies in the simplified country tables below with existing data, and calculate some indicators in order to identify policies to put in place to achieve universal access to clean cooking by 2030. So you have basically question 0, which is the simplest one, which asks you to calculate the access to clean cooking technologies as a percentage of the population. So you can assume for this exercise that improved wood cooking stoves, LPG and electric stoves are considered clean cooking technologies. So what you can do is to, so this is the table with the summary of the input data, so the data that the exercise is giving you, and you will see that you have annual data from 2015 to 2020 in terms of total population using one or the other technology. So in this case, you are just asked to calculate the percentage of people in this hypothetical country having access to clean cooking technologies. So you have been told, but if you also remember, we already touched this during today's lecture in the previous presentation. You know that the improved stoves, LPGs, and electricity are classified as clean cooking technologies, while the traditional wood stove, so the first row, is not considered as clean. So what you have to do is just to sum these values for each year. So in this case, in 2015, for example, you would have to sum 3 million, so 3 million people, 5 and 5, so this is 13 million people, and you just divide this value by the total population in each year, and you will have the values you have here in the yellow box, which is the percentage of people having access to clean cooking. And this is let's say, the first question. The second question is, which is question 1, because we started from 0, is asking you to estimate the average useful energy required for cooking annually in a household and per capita using the data and hypotheses provided. So you know the useful energy to cook an average meal in an average household, which is 1 kilowatt hour. Just give me a second. I will actually move to the Excel file, which is maybe better to see. Okay. So you are told from the exercise that the useful energy to cook an average meal in an average household is 1 kilowatt hour in this hypothetical country. Clearly, again, this is really a context-specific number. This is, in this case, let's say a random realistic number, but it's basically a random number. But this could really change depending on the country and which are the cooking habits of this country, because we could have more energy intensive meals depending on what actually people are used to cook in your country. So you have the meals per day, which is another parameter which is given by the text, which in this case is 2.2. This again could be higher, could be lower. This is an average all over the country. In this case, so it means that the average household in the country has 2.2 meals per day. This is clearly an average, because you can't have, let's say, a 0.2 meal, but this is the average because we are trying to model the entire country. On the other hand, we have 300 days of cooking home per year, and this means that since we have 365 days or 66 days per year, it means that the other days are days in which, for example, this average household doesn't cook at home, because, for instance, they can be having their meals, whether it's lunch or dinner, outside. It could be in a bar, in a restaurant, in a friend or family house. It could be in a public place because there is a community event. But on average, let's say that the average household in this hypothetical country cooks at home 300 days a year. And then we have another data which is provided by the text, which is the average household occupancy, which is very important. So here we have 4. It means that on average in this country, there are 4 people each household. So what you can do, because we are asked first to calculate the annual cooking energy per household, and this is really simple because you just have to multiply the useful energy by the meals per day, because at that point you have the energy per day, and then you multiply that energy per day by the number of days in which this household is cooking from home in the average year. So in this case, 300. So you calculate 660 kilowatt hours per year, but then the exercise also asks you to provide this number on a per capita basis. So you just have to divide this value by 4, which was the average household occupancy. So next question, if you have answer, again, really do not hesitate to ask and to write in the chat so that I can try to solve your problems in real time. So next question is, estimate the energy demand for cooking by fuel using information from the national survey and from the hypothesis. So the average annual useful cooking energy per capita. So this is a bit different exercise. So sorry. Okay. So in this case, what you're asked is to estimate the energy demand for each specific fuel. So in order to do that, you have to first start by from the information you have about each of these technologies. So for example, you have fuel wood, which is used both in traditional wood stoves and in improved stoves because they have the same fuel but different technologies. So the traditional and the improved one, which have higher efficiency. The efficiency are given by the text, so you can use them and you can see it here. And you have the annual cooking energy per capita. So in this case, you can calculate, for example, the estimated energy demand for cooking by multiplying, calculating the specific energy, the estimated energy demand for each specific stove depending on the technology, and then multiplying that value by the number of people which actually have that stove, which actually rely in cooking with that specific stove, whether it's traditional wood, improved wood, LPG, or electricity. And you will see that it's the exact same calculation. The only difference is for fuel wood, which has 2 stoves using the same fuel, but at really different efficiency because here the traditional ones have 15% efficiency, whether on the other side the improved stoves have double efficiency with it, which is 30%. You can calculate for all technologies this estimated energy demand for cooking in terawatt hours. Pay attention in this case to the units of measurement, because here we have million people and we are asking you to calculate in terawatt hours the total energy, while the useful energy and the annual cooking energy per capita is in kilowatt hours. So pay attention at all these divided by 1000, because you have to take into account, because otherwise the results will have orders of magnitude of difference with respect to the solutions you will find in the Excel file. So you can calculate this for all historical data, so till 2020. Then next question is compare reported cooking energy demand with the estimated figures, and to see actually if you see some you are able to spot some potential problems, some differences, let's say, with respect to what are the reported data, for example, in this case, from the Ministry of Energy Statistics. So these values that I'm highlighting here come from the Ministry of Energy Statistics, which told you, for example, that in the fuel wood, in terms of reported energy demand for cooking in terawatt hours in 2015 was 53.2 terawatt hours. So what you should do in order to answer this question and to see if actually there are misalignments between the model data and the reported data, is to basically divide, like calculate which is the percentage difference between this value, for example, and this value, or between this value and this value. So you will see that there is, like, the LPG and the electricity data are almost the same. We have -4%, 0%, 1%. It's nothing, let's say, really relevant. On the other hand, fuel wood is really different in terms, because we see that the estimated energy demand for cooking is actually 53% lower with respect to the reported energy demand for cooking. So this is a very important aspect that you have to take into consideration. And this discrepancy is really linked to the different efficiencies, like the fact is that it's really difficult to assess the efficiency of the traditional and also improved cookstoves across the entire country, in this case, but continent, and calculate and model, for example, the results. So this is a really, really important aspect. Last question, which is with currently stated policy on universal access to clean cooking, this country, for example, will not be able to achieve universal access to clean cooking in 2030. So you need to re-estimate the number of people relying on the different cooking technologies in 2030. Take into account this. You have to consider the following limitations. So first, the new national clean cooking plan objective is to reach 5 million households equipped with improved cooking stoves by 2030. So consider one per household. And you will have to calculate, you can go in column N and 9 and in which you will have the projections in the future, which is both in the case of the stated policy scenario and on the full access scenario. So you will have these two differences. They told you from the text that the goal is to have 5 million, 5 million households equipped with improved cooking stove by 2030. So you can go here and you will see, taking into account that there are 4 people for each household, you divide that, you multiply that 4 people per household multiplied by 1, so 5 million stoves, 1 by household, and you find out that approximately 20 million people will be relying, or are expected to be relying, on improved cookstoves. On the other hand, other assumption is that the maximum residential supply of LPG is limited by projected refinery capacity and imports at 4 terawatt hours. This is because clearly the Ministry of Energy has plans and knows, and do planning in terms of how much LPG they will be able to produce, like local national refineries will be able to produce. So how much will be imported or is expected to be imported from outside, and how much of the overall produced and imported LPG will be allocated to the residential sector, and in particular for cooking needs. So in this case, you know that this value is 4 terawatt hours. So in order to calculate the people relying in cooking with with LPG in 2030, you have to take into account the fact that value I told you in terms of annual cooking energy capacity. So by calculating, take into account also the fact that you have 4 people per household, you can calculate these 12 million people relying on LPG in 2030 in the full access scenario. But the question in this case was how many terawatt hours of electricity will be required for cooking in 2030 to achieve universal access to clean cooking. To do that, you need first to know how many people will be relying in cooking with electricity. So since this scenario was take into account full access to electricity, you have to put 0 in terms of people relying on traditional wood stoves, because we already said that this is not clean, so we have 0 here. This means that the remaining of the population will be relying on electricity. So from this value, you have to calculate how much will be needed in terms of terawatt hours of electricity in 2030, and this value comes here by doing the exact same calculation we had previously when calculating this value, but take into account the forecasted values. So that's it, and then clearly you can plot all these values, do sensitivity analysis in order to see how the results change, for example, by changing whatever parameter that we had as an assumption. For example, I don't know, maybe we could increase the number of meals per day, and you will see how much the needs in terms of energy, for example, or LPG, electricity, or in terms of fuel would increase, and etc. etc. If you want, you can also start discussing and critically have a critical look at this assumption we made. And if you have questions, you want to ask me something, feel free to do it or now during today's presentation, or otherwise you can write me in a second moment at my email that you already have. Okay, so I will move to the next part of today's presentation. Just give me 1 second. Sorry, just a second so that I can.
A review of electricity access, then discussing data, and last discussing modeling. So the world has been electrifying very fast, and you can see on this figure, starting at the year 1990, that in all regions, electricity output has increased, even more in non-OECD countries and regions like Sub-Saharan Africa. This comes from higher population and GDP with higher access, but also from higher demand at the per capita level, with each household having more appliances and more needs for electricity. Still, according to our latest analysis in the year 2019, still 770 million people don't have access to electricity and rely on stopgap and very basic technologies for basic needs such as lighting. So why does electricity access matter? Electricity access is under the Sustainable Development Goal number 7 of ensuring access to affordable, reliable, sustainable, and modern energy for all. And more specifically, it's under 7.1.1 indicator. But energy access is really at the heart of the SDGs. We often say that it is the golden thread weaving together human development, economic growth, and sustainability, because providing energy is at the base of enabling other SDGs. And we will see a few examples. Energy and electricity access is very much related to SDG number 1 of ending poverty, for example, by providing sustainable lighting products such as solar lamps instead of expensive stopgap solutions like kerosene lamps that poor households may be using. Plus, there are many relations between energy and economic development related to SDG number 8 and also to opportunities for women and SDG number 5. There are also interlinkages with climate and providing clean energy sources would displace polluting fuels such as diesel used in generators or oil products such as kerosene used for lighting. SDG 7 and energy is also very much related to SDG number 6 and 2 under the water, food, energy nexus, since we can improve agricultural productivity and water management thanks to energy. Then energy is very much related to SDG number 3 with health services benefiting from power and also with improved indoor air when there are some clean sources of lighting, for example. And last, with energy, we can get better conditions for studying at home with better lighting services, for instance, and also better schools services when schools are electrified. Let's detail a bit the relation between energy and incomes and the economy. On this figure, you can see how the share of population having access is expressed as a function of GDP per capita. And there is a strong correlation under this logarithmic curve, which means that higher levels of wealth drive higher level of consumption per capita and access to electricity, but vice versa, when we increase access to electricity, this has a potential to boost wealth. When looking at health and education, based on a study conducted in 2018, 60% of health institutions were without reliable power in certain number of geographies. And you can see discrepancies across countries. You can see countries where health centers are primarily relying on grid or sometimes on off grid solutions, and also places where there is no electricity and reliable source to power those health institutions. Coming to education, we have between 50 and 60% of schools which are unelectrified, again with strong discrepancies and with some variability in the source of power. This can come from the grid or from off-grid sources. Now let's have a look at the status of electricity access and the number of people deprived of electricity per region. So we'll start looking at the evolution over the past 2 decades. This blue space is the number of people in Africa without access to electricity, and you will see that it has increased until the year 2010 and then remained stable at around 600 million people. And when we look at other parts of the world, it is striking to see that at the beginning of the century, India and rest of Asia were concentrating almost as many people without electricity as Africa, but those numbers have sharply declined, and now electricity access is increasingly a challenge for Sub-Saharan Africa. You can look at the breakdown per region in in Africa, with of course some regions where we have important countries. We can think of DRC, which is a very heavy weight for Central Africa, or of Nigeria, which is also important for West Africa, concentrating close to 70 million people without access to electricity. So in terms of region, India was the #1 region concentrating people without access in the year 2000, but this has decreased as India reached universal access in the past years. On the contrary, regions such as West Africa and Eastern Africa have come to the top ranks of the ranking. If we look in India, but also in China, you would see here how long it took to those two countries to provide electricity to 600 million people. So in the case of China, this took 35 years. And for India, it took a bit more than 15 years. And this is the fastest electrification experience we have observed in humanity, with a very impressive um, and strong progress achieved in India. So when we see this kind of acceleration, we can expect that in Africa, it is also possible to provide access to electricity to 600 million people before the end of the decade, so in a shorter period of time, because of all the lessons learned and the technological improvements that we now have at our disposal. And there is also some very good progress observed in many countries all across the continent. Just to shed light on East Africa, we have seen in Kenya an increase by 50 percentage points in the electricity access rate between 2013 and 2018, so amounting for around 25 million people getting access. We have seen the same number of people in Ethiopia getting access to electricity, and also in Rwanda, a very strong increase in the electrification rate. So we can have a look at electrification rate in the world, and this is the other side of those numbers on number of people with or without electricity. You would see here that Sub-Saharan Africa rate for population with access is today at around 45%. So reflecting the 600 million people without electricity access. Looking with a zoom in the different sub-Saharan African regions, you can see again the strong increase in East African electricity access rate over the past few years. And you would also see the difference between different regions, West Africa being at the highest level in terms of electrification rate, whereas Central Africa has the lowest electrification rate of the continent. And on this map, you can see country by country the number of people deprived of electricity and the rate of population with the different blue colors you can see. So another way of looking at electricity access is by the fuel or the technology and the solutions which are providing access. And this is an analysis we've been doing, looking at the annual number of people gaining access to electricity by type of fuel and by technology between the year 2000 and 2012, and then between 2012 and 2015. And what you can see here is first an acceleration. On average, there were more people gaining access to electricity in the second period observed than under the first one. Then you can also see that looking at the different fuels and technologies providing access, there is a stronger role for decentralized solutions and solar PV when we look at the more recent period. But you can also see that there are some important provision of electricity to people gaining access based on coal. And this is more striking if we deep dive more into what happened in India. So this is the number of people gaining access to electricity in India over the period 2000-2016. And you would see that on average, 30 million people were gaining access to electricity every year, and 80% of them were gaining it thanks to grid extension, grid being powered by coal-fired power plant. So this is also some interesting analysis we can do, looking behind the number of people gaining access. What is the technology to provide it, and what is the fuel, the source of energy to generate those electrons? Let's have a look at the latest numbers we have at the IEA by collecting year after year and looking at every country, the numbers of people with and without electricity. So looking more specifically at Africa, this is what we observed. So a rise in the number of people without access to electricity until the year 2013. And this is because every year the demographic growth was outpacing the efforts of the governments to provide more electricity, to extend and densify the grid, or to support rural electrification programs and deployment of mini grid and solar home system. But since the year 2013, this number was decreasing, meaning that progress were faster than population growth until the year 2019, because due to the pandemic and its aftermath, we have observed that the progress are being reversed, and that in the year 2020, there are more people without electricity that, than there was in the year 2019. So this is a very concerning trend that needs to be reversed if we want to reach the goal of universal access to electricity by the end of the decade. And on the right part of the chart of the slide, you would see how those number of people without access are broken down by country, and 5 countries, so DRC, Nigeria, Ethiopia, Tanzania, and Uganda, are actually concentrating half of those African people without electricity. There are many reasons that can explain this rise in the number of people without access in the year 2020 due to the pandemic and its aftermath. Governments had to shift priorities to the more urgent task, so limiting support to some electrification program, or limiting some policy priority given to expanding electricity access. But if we look at private sector-led initiatives like mini grids and solar home system distribution, we have also seen some disruption in the year 2020 in the value chains. For example, it was more difficult to import products due to the international constraints. It was more difficult to distribute products to the last mile and in rural areas due to lockdown and containment in the countries, etc. So we have seen such difficulties preventing the progress that were observed in providing more electricity services, may it be through grid extension, densification, or through mini grid projects or solar home system distribution. An additional point is that, according to our analysis, there are people who were connected to the grid or were able to benefit from electricity access, but due to the economic consequences of the pandemic, might lose the ability to afford those services. So we estimate that in Africa, 30 million people could lose access to electricity, and by the end of the of the decade, under current policies and trends, we would expect that 630 million people would still be in the dark. Okay, now let's enter more into the definition of electricity access. So it's important to have in mind that there is no single internationally adopted definition and different ways of approaching this topic. When we discuss access to electricity, we shall bear in mind that there are different technological solutions and also several uses of electricity. So on this simplified chart, you would see different technologies, and on the lines, you would see the type of service that households and community would expect, and also more productive uses. We have basically classified it with pico solar products, such as a solar lantern that would have its independent solar panel, battery integrated into lighting systems, which might also include radio. So this type of service of product is able to provide household and community with lighting, entertainment services, especially if those devices are very energy efficient. And we are observing very fast progress in the development of such technologies with strong improvements in performances and decrease in costs. Then we have solar home systems that would include high efficient appliances like TV, fans, and would rely on as well independent solar panel plus standalone batteries and lighting bulbs, radio, torch, and other appliances. And this again can be of the use of households, but also of communities and potentially also of some productive use if it may include solar pumps, for example. Then we enter into a higher level of energy development and service with mini grids, which are small infrastructure developed at the size of a community or a village or specific needs, and who would rely on different energy sources. It can be small hydro, it can be wind, it can be solar PV, coupled with storage or coupled with backup generator, and that will be able to transmit and distribute electricity to a large set of customers. And last comes what is the most well-known and common way of providing electricity, which is the usual grid. And as you would see, the higher you go in the type of technology solution, the more services you can provide. At the IEA, we define electricity access under the below definition. Electricity access entails a household having initial access to sufficient electricity to power a basic bundle of energy services. So this, as a minimum, would be lighting devices, plus phone charging, plus a radio, plus potentially a fan or a TV, but also with a level of service capable of growing over time. So, to be more concretely, what do we consider as being access to electricity and what is not is what you can see with this red rectangle, with IEA starting with solar home system and not taking into consideration the, the smallest solar lanterns. As we just mentioned, there are different options and technologies to provide electricity access, and the main one is the grid. Still, there are some challenges coming with grid-based power systems, and just to mention one, as you would know, there are some losses which are due to the nature of how networks work. But in the case of Africa, we observe some very high level of losses, which is around 6% above the average in developing countries, with in some countries like Ethiopia or Mali, some levels of losses which can be as high as 25%. So these have, of course, consequences for the utility economics, for the power generation, and for the level of service which is provided to end customers. Another way of looking at one challenge for grids and utilities is the outages that can be observed in countries like Nigeria. Our analyses have shown that it can be up to 40% of annual outages over the year, and this can lead customers to rely on backup generators, which will be able to supply some electricity when there is an outage or a blackout of the central grid. And again, in the case of Nigeria, we have estimated that close to 20 terawatt hour of electricity was generated thanks to those backup diesel generators. Then there are other challenges for providing electricity access to all using the grid. For example, some population are under the grid, so close to grid transmission lines, but not connected. And then we have in the least populated areas and the least dense rural settlements, difficulties to extend the grid to those places. When we look at mini grids, there are also some key challenges. One of them relates to finance and economics because capex or investment cost can be relatively high, as well as opex, and especially the operation and maintenance cost. And on the contrary, revenues might be uncertain, with risk of low consumptions, low ability to pay from households, for example, or for the need for an anchor client like a telecom power or an hospital or a strong commercial or industrial customer to be the main customer, to ensure that it's economically possible to also provide electricity to smaller customers such as households. Another challenge relates to scalability because each mini grid project requires some local adjustment. It needs to be adapted to the local potential for generating electricity, be it from solar PV, from a small hydro resource, or from wind. So this needs to be customized, and in front of that, demand needs also to be well estimated based on population, future estimated demand for this specific community or settlement. So it's not easy to develop in the same time or very quickly a very large number of mini grids, even though scale is possible. And then administrative process can also be long because a mini grid is a small infrastructure, so it requires, of course, some administrative work to get, for example, license. It depends on each country context, but the deployment time can be long. And last, there are always some questions on the integration with the grid once the grid arrives. There are many ways of solving these issues, but again, it will be depend on the national context. Last, standalone systems such as solar home systems also bring some key challenges and difficulties. First, this is more about distribution than about infrastructure. To ensure that people can have at home a solar home system providing um, lighting plus TV plus fan services is a question of distribution. So the business model is more looking like what fast moving consumer goods or equipment sellers develop, rather than a business like utilities or big energy infrastructure players are used to. So it's a very different mindset. Then it's increasingly relying on digital technologies because such products that have that might have a high upfront cost are usually sold under pay-as-you-go business models, where the customer would be able to pay day after day small installments before becoming fully owner of his TV solar home system after 1 year and 2 years. But this requires mobile banking services as well as strong connectivity. Then all those products have a limited lifetime. So thinking from the beginning at recycling is key. And last, usually those solar home system distribution models have been led by private sector players who are really relying on market-based approach. So they sell to a bankable customer, and this type of approach is not adequate for everyone. So, for example, if it comes to provide electricity services to very isolated or very fragile communities like in refugee camps, such private approach are not adapted. So we estimate at the IEA that to reach universal access to electricity, we need to rely on all those solutions, grid extension as well as grid densification, but also mini grid and standalone system. And to back this statement, we have conducted geospatial analysis looking at every squared kilometer in sub-Saharan Africa, looking at where the population is, where the infrastructure are, where the existing transmission lines are, and depending on the cost of each technology, we have come with analysis on where it makes most sense and where it's more economical to develop further grid versus where it's more economical to develop mini grids or to distribute solar home system. And you can see that this type of analysis was done at the scale of the continent, but also for specific countries. And here you have the example of Cote d'Ivoire in Western Africa. Another example which confirms that full access requires integrated plans combining on and off grid is the very interesting case of Togo. So this Western African country that you can see here is not very is around 50 kilometers from west to east, but around 800 kilometers from north to south. And there is already a high level transmission line which goes from north to south. So when you think of providing more electricity services to all, you might think that it's easy and it's economical to rely on the grid and just to extend new lines from this existing vertical strong line, which is already here and which is not very far from any community in the country. But what the analysis conducted by the government show is that it's not economical and it's better to also rely on mini grids and on solar home systems. So this is the integrated strategy named CISO in Togo, which relies on extending and densifying the grid in some areas, but also partnering with private sector under license schemes to develop mini grids and solar home systems. We will now discuss data collection, reporting, and indicators for access to electricity. So first, there are many barriers and limitations to tracking access to electricity and off-grid. Some of them relate to survey and sampling techniques. Other relate to the off-grid source of electricity, like mini grids or solar home system, which, for example, are not metered or do, would present difficulties in giving some data in terms of capacity or electricity generation. Then calculating the rate of electricity access itself would involve many parameters, looking at binary information or gradual and tiered level of access, looking at the source of access, looking at per capita power consumption, or tracking also the lifetime of equipments to ensure that access is maintained over time. There are mainly two two sources for tracking electricity access, and this is what is currently done today. The first source are surveys, and this is reflecting a demand size vision of access with DHS or local demographics surveys asking to households their source of lighting and getting an understanding whether households have or have not access to electricity and which source is providing electricity, grid, mini grid, solar home system. This is a survey, so it's not updated every year, and samples need to be carefully selected. But it gives a very good field and bottom up view of electricity access. And this is what the World Bank is using, for example, in its database. The second source, and which is what the IEA has been using, are government reported supply side data, mostly coming from the utility, and that can be updated every year based on the number of connections, based on the number of lines and meters that utilities would know. And it can also take into consideration off-grid data such as rural electrification government-led programs or even data coming from the private sector. This is more reflecting a supply side vision of access. Then there are new types of data, new methodologies which are currently developed, and the IEA is also very much working on improving the understanding of electricity access. So we are looking for more data on the type of connection, the availability of electricity, reliability, also information related to finance and affordability from the household perspective, quality of the electricity, cleanness, or in other words, what is the source of power generation behind the technical option. And this can come through better surveys with more specific and detailed questions or more granular data from programs and energy providers. Then, beyond households, there is also interesting work being done to understand better how health centers, public buildings, or schools are connected to electricity. One example developed by the World Bank is a multi-tier framework, so it's still relying on surveys and it enables to understand different tiers or level of service of access to electricity rather than a binary information of household has or has not access to electricity. There are also increasingly off-grid data which are developed and which are feeding some consolidation and data tracking systems. Here is an example in Zambia under the Edison platform related to a grant program where there is a live tracking of solar home system and mini grid connections relying on smart meters and other tracking technologies developed by those solutions. Then there are also increasingly geospatial and satellite data that can help track better access to electricity using nightlight images, day PV panel recognition, or also electricity networks maps. Now we will discuss modeling of access to electricity, or how can we make projections on how electricity access will evolve in the future. So, as always, when we do some modeling exercise, we need to start by wondering what question do we want to answer. And here, again, we can take a scenario approach with deductive scenario. What will the future will look like under certain hypotheses? For example, if the current announced policies are effectively implemented, if the known technologies are developing as we expect, Or we can take a normative approach. What is the pathway if we want a specific future to meet given targets? For example, what's the trajectory between now and 2030 if we want universal access to electricity by the end of the decade? So when it comes to access to electricity, some questions we want to answer are how many people have access today and will gain access every year in the future? How much electricity demand will come from those newly connected households, and how will that feed the overall demand for electricity? Then, once we know demand, we can look at supply and see how this demand will be supplied, how we will match this level of electricity demand, and by which portfolio of solutions. Again, it can be on grid or off grid, and by which type of fuels. We can have questions related to investment. How much investment will be needed to serve the demand? And we can also investigate impacts and see, for example, what are the energy access related CO2 emissions. Here we will present very synthetically how we do this kind of modeling exercise at the IEA under the World Energy Model. So we have first an electricity access database tracking all the policies, looking at electrification projections on the one hand, and on the other hand, we have information on consumptions level per capita. Based on those two, we'll be able to estimate what the additional electricity demand due to access or to new population gaining access to electricity will be in the future. And we'll be able to allocate this electricity access to different sub disaggregated services behind our residential module modeling. So will that demand will be for lighting, for cooking, for powering appliances, for water heating, etc. And we will be able to allocate all this in specific energy services. Then comes the power generation module where we look at what supply can match this demand. And to do that, we have developed, based on geospatial analysis, some um, some modeling work to understand what is the best mix of solution, grid extension, grid densification, mini grid infrastructure, or solar home system to meet this future um, demand for electricity. And with that, we will get information on demand by each solution and reflected into both generation terms and capacity terms. Let's have a look at a few examples of those results of the modeling outlook. Here you can see electricity demand in 2018 in Sub-Saharan Africa and how it would evolve in the coming decades depending on the scenario, and also looking at what is the demand coming from people already connected to electricity today and from people gaining access, and then what's the demand for non-household productive use or transport. We can also modelize efficiency savings. So what will be the demand if we take into consideration strong energy efficiency policies and more efficient appliances and equipments, or if we don't. Another example on the results of our modeling is on the power reliability. As we discussed, we know that in Africa today, many countries are experiencing a certain level of outages, of transportation and distribution losses, and as a result, a high number of backup generators used by consumers. All these elements would evolve in the future. Again, we are getting projections under our different scenario as output of our modeling exercise on electricity access. Investment is also an output of the modeling exercise. We will see for different regions what are the required annual investments in access to electricity under a stated policies or steps scenario taking into account announced policies, or under a sustainable development scenario that was, let's say, equivalent to the Africa case, where we reach universal access. And this kind of investment can be broken down: technology, grid, and off-grid solutions. A last example is on the effects of the access results on greenhouse gases emissions. And here, this analysis can consolidate our projection on access to clean cooking and on access to electricity. So let's have a look in the stated policy scenario. What are the emissions related to cooking and to electricity under the stated policies at the end of the decade? To go from the stated policies to between today and 2030, we see that we will have a reduction in traditional use of biomass that would limit the growth of greenhouse gases emissions. Under a sustainable development scenario, we have a higher level of emissions because of more people using LPG, because of more access to electricity, which will also be generating greenhouse gases emissions. But with more people shifting away from traditional use of biomass, we have a net negative change, meaning that under a scenario where everyone has access to both electricity and clean cooking, there are less there are less CO2 and methane emissions than under today's situation. So universal access will not be at the expense of climate and of emissions.
Okay, perfect. So sorry for the delay. We had a bit of delay because of the previous sections. Just to finish, I wanted to show you, you already have seen previously in other webinars and also in today's presentation, this chart, which is the least cost electrification strategy for the entire continent. And this is something we are working on. And you will also see a new version of it in the Africa Energy Outlook that we will be presenting and publishing this year, probably in June. And you will see the results here. And this is really related to the questions I also ask you in Menti through Mentimeter. Which do you think is the best solution in order to guarantee access to electricity to all citizens in Sub-Saharan Africa? And as you can see, there is a mix of all technologies. It really depends on where you are, how far you are from the existing grid, which are the renewable energy sources locally present, which are the sectors that could be developed, which are the economic sector that electricity could fuel and could boost. So let's say that's it. We could have questions and answers session. If you have any question, as usual, feel free to write in the Q&A box in the chat or to raise your hand and I can give you the floor. In the meantime, I remind you that next week we have the next lecture, which is on Wednesday, which will be, let's say, the official last lecture in terms of theoretical contents. We will be working on solid biofuels estimation models. And then Thursday, we will close the session. So this first phase, and I will give you a bit more information with respect to the next phase. Okay, so I don't see any question, neither comments, neither raised hands. So I would close here the session. Wish you a pleasant evening and weekend starting from Saturday, and see you on next week. Thank you very much.